similar to what we had with an arithmetic sequence, there is a quick, short way to add up the first however many terms of a geometric sequence. So the sum of a finite geometric sequence is found by using, well, if you have the terms a sub 1 times r, in other words, the second term, or a sub 1, and a sub 1 times r squared, the third term, etc., etc., etc. As long as your common ratio is not equal to 1, the sum s sub n is given by, well, going from your first term to your nth term. This is, again, just how we find each individual term. It's going to be a sub 1, your first term, this whole block here, times 1 minus r to the nth power over 1 minus r. Seems kind of complicated. Let's try this out. So the summation of geometric sequences, which are created using ratios, are surprisingly simple in this case. Instead of having to find like all the terms, we just kind of plug in some numbers. So in the first one, a sub 1 from I equals 1 to 12 of 4, and we find each term by doing 4 times 0.3 to the I minus 1. We got to find the first term, a sub 1, and we're going to do that by plugging in 1. So we have 4 times 0.3 times, or raised to the 1 minus 1. So that's 4 times 0.3 to the 0. Well, 0.3 to the 0 is 0, so, or sorry, 1, goodness gracious, times 4 is 4. So our first term is 4. The r value, we're already given that. That's the number that's raised to the exponent, so that's 0.3. And then the n value is however many terms we're adding up. We're adding up the first 12 terms. So if we just start plugging that in, using, again, that formula that's in the box up there, a sub 1 we found was 4. We're going to do 1 minus 0.3 to the 12th power over 1 minus 0.3. Now, folks, that seems like a nightmare to try to do by hand. I would strongly suggest just using a calculator, where you put that in parentheses and that in parentheses as well. When you type it into a calculator, I maybe should even put a squiggly equals because we're rounding it. It's going to be about 5.714. Now we have a similar problem off to the right there. The only thing that's different is the exponent is just I. It doesn't have an I minus 1. Curious. So we're going to find our first term again. So we'll do 4 times 0.3 to the first power. Well, that just makes it 4 times 0.3, which is 1.2. The second part we need, well, we need something to figure out our r, which again is whatever's being raised to the exponent. It's 0.3. The n is still 12. So similar to what we had, it's going to be 4 times, well, nope, sorry, not our first term. Our first term in this case is 1.2 times 1 minus 0.3 to the 12th power over 1 minus 0.3. Again, we can type that into a calculator. We end up typing it in. We end up rounding it to 1.714. Now, one notation I didn't include, this is the 12th partial sum, so that'd be s sub 12, same for the other one. Now, these numbers share the decimal places. Not really a coincidence in this case. We'll talk more about that in just a second. Speaking of which, infinite geometric summations. So it doesn't really make much sense to calculate the sum of an infinite arithmetic sequence because you're just adding up integers or adding up things that keep on getting bigger and bigger and bigger, or smaller and smaller and smaller. So it's going to go larger and larger and larger. So it's going to get really, really positive or really, really negative. That's your only options. Geometric sequences, however, we can do this. If you have a common ratio between 0 and 1, we can do an infinite geometric series. So if what you're adding becomes less and less, it becomes smaller and smaller, you'll eventually reach a finite limit. So imagine we're dealing with that formula for the finite sum, a sub 1 times 1 minus r to the n over 1 minus r. Now, if the absolute value of r, so it could be positive, could be negative, whatever it is, if it's small, it's less than 1, then what's going to happen to the r value if the numerator, as n becomes larger and larger and larger? Hint, let's talk about this pattern here for a second. What's the pattern where we take 0.5, so let's pretend that's our r value, and raise it to larger and larger values. So like 0.5 squared is 0.25. 0.5 to the third is 0.125. 0.5 to the fourth is 0.0625. 0.5 to the fifth, this one I actually don't know off the top of my head. I probably should check that. 0.5 to the fifth power is 0.03125. You'll notice the values are getting smaller and smaller and smaller. In other words, as n gets bigger, r to the n gets closer to 0, which in turn means the numerator gets closer to 1. If it's 1 minus r to the n, and r to the n is pretty much 0, then the numerator is just going to be 1, which is going to tie in directly to the formula we're going to use for an arithmetic, or goodness gracious, an infinite geometric series. So, with that in mind, the sum of an infinite geometric series, if your r value is teeny, if it's between 0 and 1, could be positive, could be negative, we're just talking about absolute values, then the infinite geometric series, where again you're multiplying by that r over and over to get from your first term to your second term to your third term, is going to look like this. The sum of the first, or of an infinite number of terms. You'll notice there's no subscript on this s. It's just, it would be like s sub infinity. But again, you're going from term 0 up to infinity. The formula we're going to use is a sub 1 times 1 over 1 minus r. Remember, we said as n gets closer and closer to, or gets bigger and bigger and bigger, r to the n gets smaller and smaller and smaller, gets closer to 0. Another version of this formula that you'll often see is a sub 1 over 1 minus r. That's the one I'm more familiar with. That's the one I've used more often. So we've got a couple examples down here. For this first one, we've got going from 0 to infinity of 4 times 0.6 to the n. Again, we just got to find really two pieces now. We got to know our first term, and we got to know r. Well, the nice thing is the r value is usually pretty easy to figure out. It's just whatever being raised to the exponent, so that's 0.6. The first term, in this case, that's a sub 0, is going to be 4 times 0.6 to the 0th power. Well, 0.6 to the 0 is 1, so it's really 4 times 1, which is just 4. Now again, I'm going to use this formula just because it's a little quicker. We're going to put a sub 1 over 1 minus r, which would be 4 over 1 minus 0.6, which gives us 4 over 1 minus 0.6 is 0.4. Now 4 divided by 0.4 gives us a grand total of 10. So if we're to keep adding up those values over and over and over, the first term plus the second term plus the third term, we'd end up with the answer of just 10. Now you can check that on a calculator. Just keep finding consecutive terms, keep adding them. They're going to get closer and closer and closer to 10. Similarly, for example B, we got to find our first term, in this case the 0th term, which is going to be 2 times 2 over 3 to the 0. Well, that's just 2 times 1, which is just 2. R, again, is just whatever's being raised to the exponent. It's 2 over 3. So plugging this in, we got 2 over 1 minus 2 over 3. Well, 2 over 1 minus 2/3, that's 1/3. Dividing by a fraction is kind of rough, so let's take that, instead of dividing by 1/3, let's multiply by 3 over 1. So we got 2 times 3 over 1, in other words, 2 times 3, which means we get a grand total of 6. So the sum of all the terms in an infinitely long series, in this case, is just 6. Let's try one more, one that's just kind of written out as a sum anyways. We got 9 plus 6 plus 4 plus 8/3 plus etc., etc., etc. This case, it's going to be a little easier for us to find our first term. It's just 9. Now, the ratio is going to be the one that requires a little bit more work. It's really take any two consecutive numbers and divide the second one by the first. So 6 divided by 9 gives us 2 over 3. Also, if you wanted to check just to make sure, I'm going to take the third term, 4 divided by the previous term, 6, which again is 2/3. So our r value is 2/3. So the sum, if we keep adding these over and over and over, is going to be the first term, 9 over 1 minus 2 over 3. So we got 9 minus 1 minus 2/3 is 1/3. Now again, dividing by a fraction is not the easiest thing to do, so we're going to take it and do 9 times the reciprocal, 3 over 1, which gives us a grand total of 27. So we're adding up an infinite number of terms and getting a finite answer.